Today we are going to learn lesson 6, solving polynomial inequalities. So first, let's have a look at today's learning goals. After this lesson, you will be able to understand the common steps to solve polynomial inequalities, and solve real-world problems that involve polynomial inequalities. Okay, today's lesson is broken into two parts. First is to solve polynomial inequalities, and the second part is to deal with real-world problems that involves polynomial inequalities. Okay, so first of all, let's have a look at the common steps to solve a polynomial inequalities. Suppose px is a polynomial function, then px equals or greater than 0, or px greater than 0, or px is less than or equal to 0, or px is less than 0 is a polynomial inequality. So the common steps to solve polynomial inequality are listed below. First, usually we need to simplify the inequality to a form like this one, this one, this one, or this one, where px is a polynomial function using okay, usually we do the simplification using equivalent transformation. So after the transformation, the new inequality must be equivalent to the original one. Next step, find all the zeros and corresponding orders of px by factoring or using technology. Next step, sketch the graph of px, considering its properties such as degree, the leading coefficient, the zeros, etc. And last, determine the intervals that satisfy the inequality. Okay, so next, we'll use this example to illustrate how we can solve a polynomial inequality using the steps mentioned above, right? Okay, so now we have an inequality like this. So first of all, we need to simplify this. So note that we can divide both sides using a 2, right? Because 2 is a positive number, so that means we don't change the inequality symbol here, right? So the original inequality is equivalent to minus x cubed minus 3x squared plus 6x plus 8 less than or equal to 0, right? Okay, so usually to make things simpler, we can then multiply both sides using a -1 in order to have a positive leading coefficient, right? So this step is actually optional, depends on you. For me, I like to make the leading coefficient be positive in order to make things easier. All right, so next, you can just let px equals x cubed plus 3x squared minus 6x minus 8, right? And then we want to find all the zeros. Okay, so we need to factor px, right? All right, if this is not very easy to factor, remember that we can always refer to the factor theorem along with integral zero theorem, right? So we need to check all the factors of the constant term, which is positive or -1, positive or -2, or positive or -4, or positive or -8. Check these numbers. If these numbers can make this expression be 0, right? And we can actually find that x equals 0 is a 0 of px, right? And then we know x minus 2 is a factor of px. So in order to find the other factor, usually we'll perform a long division, right? Okay, so that means the other factor is x squared minus plus 5x plus 4. All right, let's call the inequality here asterisk. So the asterisk is equivalent to left-hand side can be factored to x minus 2 times x squared plus 5x plus 4 greater than or equal to 0, right? And the later part is apparently factored to x plus 1 and x plus 4, right? Okay, so in this way, we successfully factored the original inequality to this factored form. So now note that there are 3 zeros, right? So let's draw a sketch of the graph of the function px. We have a 0 minus 4 and another 0 minus 1, another 0, x being 2, right? And note that the leading coefficient is positive, right? So for okay, let's write it here. Leading coefficient is positive and the degree of this polynomial is 3, right? For a odd number degree, the function will look like this or this, right? And also note that leading coefficient is greater than 0, so the function will have a pattern like this, right? So that means it will extend from the third quadrant all the way up to the first quadrant here, right? Okay, so when it comes -4, -4 is a 0, right? And it's a 0 with with an odd number order. So the function will change its sign. So it crosses this point and then comes to the next 0, -1. -1 also has a odd number order. So the function will change its sign all the way down and then to the next 0, x being 2. X being 2 is also having a odd number order, right? So the function will change its sign, then extend all the way up in the first quadrant, right? Okay, so the function will have a pattern like this. And then we know that we need to solve all the intervals that makes this function greater than or equal to 0, right? So the solution must be from here to here, right? And the other interval is from here to here. Okay, so that in this way we know that the solution is x is greater than or equal to 4 or less than and less than or equal to -1, or x is greater than or equal to 2. Understand? And sometimes you can also use interval notation. That means if you use interval notation, the solution is -4 to -1 inclusive union with 2 to positive infinity. So you could write either way, okay? Also, both of these two ways are correct. Okay, so a nice writing of the solution is illustrated in this slide and next slide. You can check this after the class. All right. Okay, do you have any questions? No? Okay, so let's do a practice. This time, you will try to solve this inequality by yourself. Okay, I'll give you 3 minutes to solve this question. All right, have you finished? Okay, let's have a look at how to solve this. This is actually a quadratic function, right? Quadratic inequality. So first of all, we can let fx be x plus 3 times 2x minus 3, right? And it can be seen that the rows are x equals minus 3 and x equals 3 over 2, right? And both of the zeros have order 1. And we know that the sketch of this function will look like something this or this, right? Because it has a leading coefficient be positive and a degree of even number, right? Okay. If the leading coefficient is positive and if it has an even number, it will have a pattern like this, right? Because all the zeros also have odd number order. So the function does change its direction at both of the zeros. All right, so what are the intervals that can make this function greater than 0? Of course, there is an interval here and there is another interval there, right? So the solution is x is either less than 3 or greater than 3/2, right? This is our solution. Or if you are familiar with the quadratic function, you can directly sketch its graph because it will look like either this way or this way, right? But it only applies to quadratic function. If the degree is higher than 2, you need to analyze its graph by analyzing its leading coefficient along with the degree, all right? Okay, so let's have a look at the next practice. This inequality here is more complex, right? So I'll give you 3 minutes to think about its solution. All right, let's have a look at the solutions together. Okay, so first of all, we can let px equals x to the power of 5 minus 2 times x to the power of 4 minus 9x cubed plus 14x squared plus 20x minus 24, right? And we want to sketch its graph. And first of all, we want to find its zeros. So note that this is a complex polynomial, so it's better to use a factor theorem, right? All right, by factor theorem and the integral zero theorem, we need to check all the factors of the constant coefficient, which are minus or positive 1, positive, negative 2, or 3, or 4, or 6, or 8, or 12, or 24. And then check if these numbers can make px be 0, right? So let's start with 1. So apparently when you put 1 in there, you will get a 0, right? So because p1 is 0, then x1 is a factor of px, right? So in order to find the other factor, we can just use the long division. All right, so for this particular question, before we use the long division, note that the degree is so high that even if we use the long division, we'll get x to the power of 4, something like that, right? So we'll use the factor theorem again. So it's better to find another factor before we use the long division. All right, so when you check x being 2, you will get actually p2 is also 0, right? So we know that x minus 2 is another factor of px. Okay, so then we know that x minus 1, x minus 2 is a factor of px, which is x squared minus 3x plus 2, right? And this time we can use the long division like this to find the other one. Okay, first of all, we can put a x to the power of 3 here. Okay, so now we know that the other factor is x cubed plus x squared minus 8x minus 12, right? Okay, so basically px is x minus 1 times x minus 2 times x squared plus x x cubed plus x squared minus 8x minus 12, right? Okay, again, let's use vector theorem and the integrals zero theorem to find all the factors of the later part. So note here, when you put 3 in there, you will get 27 plus 9 minus 24 minus 12, which is also 0, right? So minus 3 is a factor of the last term, the last factor. So let's use the long division again to find all the factors of the last factor. Okay, as we can see here, the third factor here can be further factored to x minus 3 times x squared plus 4x plus 4, right? And note that x squared plus 4x plus 4 is square of x plus 2, right? Okay, so px can be factored to x minus 1 times x minus 2 times x minus 3 times x plus 2 to the power of 2, right? Okay, next, we need to sketch the graph of px. Okay, so px has 4 zeros. First, a 0 of minus 2 with order of 2, right? So order 2. And then 1, 2, 3, right? And also note that this polynomial has a degree of 5. And leading coefficient is positive, right? For degree of 5 and leading coefficient is positive, this function will have a pattern like this, right? It will extend from the third quadrant to the first quadrant. So it comes from all the way here, goes all the way up there, right? So first of all, when it comes to a 0 of minus 4, note that minus 2 has an order 2, right? For an even order, this function does not change sign, so it bounces back. And then when it comes to a 0 of 1, 0 of 1 has order 1. 1 is a odd number, so this function will change sign, and then all the way up to 2. 2 also has an order of 1. 1 is odd number, so this function will change its sign here. And then when it lands on the next 0, 3, next 0, 3 has a order 1. Order 1 is a odd number, so this function will change its sign here and extend all the way to the first quadrant, right? So basically, the function will have a sketch like this. So now we can determine its interval that can make the function less than 0, right? So it must be this one here, and this one here, right? And so the final solution is x is less than minus 2, or x greater than minus 2, less than 1, or x is greater than 2 and less than 3, right? This is the final solution. Okay, please have a look at this. Do you have any questions? And a clearer solution is illustrated here. You can read it after the class, okay? Have a look at this. If you have any questions, please let me know. Okay, if you don't have any questions, let's see the next practice. Okay, solve the inequality x to the power 4 plus x cubed minus 3x squared minus x plus 2 is greater than 0. I'll give you 3 minutes to solve this question. All right, have you finished? Okay, this time we can let px be the expression on the left-hand side. And actually, we want to find intervals that can make px is greater than 0, right? Okay, so this time we can use factoring by grouping technique. So note that we can split the third term to, split the fourth term to minus 3x in order to have a x plus 1, which is might be the common factor, right? So minus 3x, in order to have the minus x in the original expression, you need to compensate a positive 2x, right? And then let's group these two terms, and these two terms. Okay, as you can see here, x plus 1 is a common factor, right? And what's left there is x cubed minus 3x plus 2, right? Okay, so next we need to factor this expression, right? So this time there's no better way to do this. So we can consult the factor theorem along with the integral 0 theorem, right? So note that when you put a 1 in, 1 minus 1 cubed minus 3 times 1 plus 2 is 0, right? So x minus 1 must be a factor of x cubed minus 3x plus 2, right? So we can use the long division to find the other factor. If there is no term of x to the power of 2, so that coefficient is 0. Okay, so apparently the other factor of the later factor here is x squared plus x minus 2, right? Okay, so we know that px is x plus 1 times x minus 1 times x squared plus x minus 2, right? And this can be further factored to x plus 1, x minus 1 times x plus 2 and x minus 1, right? Which is x minus 1 to the power of 2 times x plus 1 times x plus 2, right? And then we can sketch the graph of this function. So it has 3 zeros, right? Which are minus 2, minus 1, and 1. And 1 has a order 2, right? Okay, so also note that this function has a degree of 4, right? And the leading coefficient is also positive. So for a degree of 5, this function will either have this shape or this shape, right? And because the leading coefficient is positive, so it must have a pattern like this, right? Okay, so it all the way from second quadrant extends to the first quadrant, right? And when it arrives at the first zero, minus 2, note that minus 2 has an order 1, right? Order 1 is a odd number, so this function will change its sign here. Sorry, this is a poor drawing. To redraw this. And then when it arrives to the next zero, note that next zero is x being -1, which also has an order of 1, and 1 is a odd number, so it will extend, will cross this point, right? And next 0 is 1, because 1 has order 2. 2 is a even number, so this function will not change its sign there. So this function will have a pattern like this, right? Okay, so what are the intervals that can make the function greater than 0? So it must be here, here, or here, right? Okay, so the solution is x is either less than 0 or x is greater than -1 and less than 1, or x is greater than 1, right? This is the final solution. Okay. All right, a formal way of writing the solutions is also illustrated here. You can spend some time reading it, and if you have any questions, please let me know. Okay. All right, so next let's have a look at an example of solving real-world problems involving polynomial inequalities. Okay, so let's have a look at this example. A rectangular in-ground pool is to be installed. The engineer overseeing the construction project estimates that at least 1408 cubic meters of earth and rocks need to be excavated. What are the minimum dimensions of the excavation if the depth must be 2 meters more than 1/4 of the width, and the length must be 12 meters more than 4 times the width? All right, so from this expression, we know that, suppose we use 3 letters to denote the height. So usually you can draw a diagram to illustrate this question, right? Suppose this is a sketch of this pool. And this is the height. And this is our length, L. And this is our width. We use a W to denote it, right? Okay, so basically we have the information like this. We know that H is 1/4 of the width. Plus 2 meters, right? And the length is 4 times the width plus 12 meters, right? And of course, all the dimensions must be positive, right? You can't have a negative dimension. Okay, so total volume is height by width by length, right? So L, W, H, which is 4W plus 12 times W times 1/4 quarter of W plus 2, right? And then we can simplify this expression, which will get you W cubed plus 11W squared plus 24W, right? Okay, so the requirement is total volume must be at least 1408, right? At least means greater than or equal to 1408. And this should be equivalent to W cubed plus 11W squared plus 24W greater than or equal to 1408, right? Okay, so this is equivalent to W3 plus 11W squared plus 24W minus 1408 greater than or equal to 0, right? Okay, now we need to find, we need to factor the expression on the left, right? So usually if it cannot be directly seen, we used to use the factor theorem along with the integral zero theorem, right? We need to check all the factors of the constant term to see if that is one of the possible zeros. So we can start with number 1 or 2 or 3 and etc., right? Sorry, 3 is not a factor, so we don't check 3. So let's check if you put 1 there. 1 is apparently too small, right? 2 is also too small. So how about 1, 2, 3, 4, 5, 6, 7, 8? So you can just keep trying. When you are trying 8, so actually 8 cubed plus 11 times 8 squared plus 24 times 8 is actually 512 times plus 704 plus 192. So minus 1408 minus 1408. So this is actually 1408, right? So when you put 8 in there, you will get a 0. So that means W minus 8 is a factor of W cubed plus 11W squared plus 24W minus 1408, right? Okay, so we can use the long division to find the other factor. Okay, divided by W minus 8. So we can put a W squared here. And then we can put a 176. 176W minus, so 176 times 8 is 1408. So the other factor must be w squared plus 19w plus 176, right? So here, let's call this asterisk, which is equivalent to w minus 8 times w squared plus 19w plus 176 greater than or equal to 0, right? So let's check if this expression here can be further factored. So apparently this is a quadratic function, right? So we can use a determinant. Determinant is 19 squared minus 4 by 1 by 176. Okay, so apparently this is smaller than 0, right? Once the determinant is smaller than 0, that means this function here has no zeros. So it cannot be 0. That means cannot be factored. All right, so that means the only solution is w equals 8, right? So if w is 8, we know that the height is 4. And the length is length is how many? 44, right? And the units are meters. Okay, so this is our final solution. Okay, please have a look at that. Also, you can read formal writing of the solution in this slide. Okay, any questions? Please let me know. Okay, if you don't have any questions, let's do a practice. So this time, I'll give you 5 minutes to think about this question here. All right, have we finished? So let's have a look at the solutions together. So basically here we want to solve for t such that the price p is more than $90, right? So we can just let p t be more than 90, right? Which is equivalent to 0.t cubed minus 5.5 t squared plus 14t minus 90 greater than 0, right? And usually making the coefficient integer can probably make the problem easier, right? So we can multiply both sides using 2, right? So it becomes t cubed minus 11t squared plus 28t minus 190 greater than 0. Okay, so let ft stands for the function on the left hand side. And then actually we want to factor ft, right? Again, usually you need to consult the factor theorem along with the integral theorem. So note that when t is, so let's check which number you should test. You should test all the factors of minus 180, right? So if you put a 1 there, that's too small, right? You can check all the way from 1 to 10. So let's check 10. So when t is 10, ft is actually 10 to the third minus 11 times 10 to the power of 2 plus 280 minus 280, right? This is actually 1000 minus 1100 plus 100, and it happens to be 0. So t is 0. T is 10 is 0 of ft, right? So that means t minus 10 is a factor of ft. And also, the other factor can be determined using the long division. Okay, t minus 10, we can put a t squared here, t cubed minus 10t square minus t squared plus 28t. And then we can put a minus t here and minus t squared plus 10t and 18t minus 180. We can put a 18 here, right? 18t minus 180, which gives you a remainder of 0. So the other factor is t squared minus t plus 18, which can be easily factored further, right? Okay, so ft can be factored to t minus 10, and then t squared minus t plus 18, right? Okay, now you can check if this expression here can be further factored. So note that the delta determinant is 1 minus 4 times 18, which is apparently less than 0. So there's no zeros for this quadratic, right? Okay, so that means it cannot be further factored. So let's call this asterisk. Asterisk is equivalent to t minus 10 and greater than 0, right? Okay, so that means, so note here, for this quadratic, it opens up and it has no zero. That means it will have a graph like this, right? This means it is always be positive. So we can divide both sides using this quadratic. The original inequality is equivalent to t minus 10 is greater than 0, right? Okay, so this is actually t is greater than 0. So this is our solution, right? So that means when t is greater than 0, the stock price is more than 90, right? Okay, so the conclusion is from 2010 on, the price is more than $90. Okay. Also, you can check a clearer writing of the solution on this slides after the class. Okay, do you have any questions? All right, if you don't, let's make a summary of today's class. So after today's class, now you should be able to understand the common steps to solve polynomial inequalities. And then you should also be able to solve polynomial inequalities and solve real-world problems that involve the polynomial inequalities. So the key to solve a polynomial inequalities is to find the sketch of the graph of the function, and by analyzing all the zeros with their orders, you can find the intervals that can make the inequalities be true, right? And for real world problems, there is one more step. You need to convert the problem stated in natural language to a model that is stated in mathematical language. And after that, you can just solve that mathematical model, all right? Okay, so that's all for today's class. And